Hi there, and welcome to another web snippet brought to you by the guys here at Innova Systems. My name's Matthew, and this time I'm just going to have a little discussion about using non-uniform pressure distribution within SolidWorks Simulation, with particular reference to a hydrostatic pressure situation. So let's have a look at the model. Okay, what we've got here is a pretty simple model of a boat. We've got some rib structures inside, a plank where you might want to sit. And what you'll see I've done is I've generated a plane, here I've labelled water, and used that to split all the way around the outer face of the boat. And this is what's going to represent the water line against the outer face of the boat. You'll also notice that I've got a coordinate system set up over towards the rear of the boat. And this was generated by selecting a vertex shared by the corner of the boat and that water plane. And this will come into significance when we move into setting up our pressure distribution. Okay, so let's set up a study. And I'm just going to call this hydrostatic pressure. And you'll see we've pulled through into the study now. First thing you'll notice is that I've already specified a material. Hopefully you'll know how to do that by now. And next thing I'm going to do is apply a fixture. So in this case, I'm just going to use a fixed geometry and come in and grab the very top face of the boat, because that's pretty distanced from where we're expecting to see our large pressures. So we're going to allow that area to be fixed. Now the only thing that remains for us to do is to set up our non-uniform pressure distribution. And that's done by right-clicking on the external loads and selecting pressure. What you'll notice is that we've got a tick box down the bottom here, which if we enable expands to reveal the equation coefficients options for our non-uniform distribution. So just to explain a little bit about that, let's just switch back over to the presentation. And so here you'll see how these inputs generate the pressure for us. So first of all, you'll notice in the top box here I've specified a pressure value of 200 newtons per square meter, or pascals. Next, we'll grab that coordinate system, which is what we specified within our model, and then we add numbers which represent our equation coefficients. So here you'll see how this translates to an equation. The 200 is our multiplier, and then each of these coefficients becomes either a singular value, as with the 1 here, or a multiplication factor for each of the coordinate values, so x, y, xy, x squared, and y squared. Now, in reference to the situation we're looking at here, we've got hydrostatic pressure. So if we consider a fluid volume which is being held by a container of some sorts, which to the outside is exposed to air, we have the atmospheric pressure or ambient pressure on both the outside face of that vessel and the internal face. So those cancel each other out. And what we're left with is that pressure distribution which builds up as a result of our fluid, which is hydrostatic pressure. And that pressure is proportional to the density of the material, so here water, which has a density of 1000 kilograms per cubic meter, gravity, which is an acceleration of 9.81 meters per second squared, and h, which is the depth from the free surface. So if we are to consider our exact situation, if we take the top free surface as our datum, i.e. y equals 0, then our pressure is equal to 1000 times 9.81, which is 9810, times y, which is the distance downwards from that datum. So applying that to our model now, what we will do is come in and grab our coordinate system and specify our 9810 newtons per square meter in our pressure value box, and then change these equation coefficients so that we are simply proportional to y. Then all we need to do is select the faces upon which to apply our pressure, and that's where that split line comes in. So now we can select solely the bottom of the boat. And that's our pressure distribution set up. So here you'll see these arrows indicative of the pressure value start very small right up by the water level and increase in size down towards the bottom of the boat where they reach a maximum, where we would expect to see the maximum hydrostatic pressure. So finally, all that's left to do is generate our mesh. And I'm just going to use some values that I've had a look at and determined beforehand. And then all that's left to do is click run. And so we have our results. Obviously, we would expect to then go on and conduct a results convergence study by refining that mesh and continuing to solve to make sure that our results have reached a steady level. But that's going to take a bit too long to feature on the video. So let's stick with what we've got. So here we can see how that pressure has impacted our boat. Clearly we've got an exaggerated deformation scale. You can see how the pressure builds up more on the bottom than the top, which is as you would expect. And that's about all I've got time for in this short video, so please join us again soon. If you wanted to get in touch with us, you can do so by visiting our website, which is www.innova-systems.co.uk, popping an email over to the support address at support@innova-systems.co.uk, or giving us a call on the number you see on your screen now.